Okay, morning everybody. Let's begin today's class. First lecture, official. So we're going to talk about chain conformation in polymers. Particularly, we will discuss about why we want to study chain conformation and what kind of technique out there you can study those chain conformation and what kind of model is out there. Okay, so I'd like to give out a goal of study. So the object for this chapter is to help everybody understand how a single chain behave in nanoscale. Okay, so imagine that, like we talked about, if you're a nanoman, you dive into the nanoscopic scale, what does a chain behave? How do you sit around your neighbors? If you look around, you have your friends sitting in the same classroom. So we want to ask the same question: how does the chain behave in solid states? And that's not an easy task because we don't have a ruler. We can measure it directly. And a lot of times, those are entangled together. So first part of the question is, how do we king up some model we can study single chain conformation? So, give you some idea. Let me pick a random cable. Okay, this is going to be my victim today. So, imagine, in the other day we told a short pole, everybody thinks they will be coiled. So, this is the case if you look at the macro scale in our real life. That's your chain. It looks like a coil, we can measure it. But nanoscale is very hard. So we need to king up some ideas how to study those materials. So for today's lecture, we're going to talk about a few terms, how we can describe a single polymer molecular chain. Okay, so the goal is to define a few size scale, a few dimensions, so that we can help everybody familiarize how big the chain is. We continue the discussion about what we talked about the other day. So a molecular size depends on the molecular weight. So higher the molecular weight, you're going to be bigger. There's infant size molecular for polymer. There's adult size. Then there's the giants. So they're going to be much, much bigger. So in the range, what we're going to discuss is usually somewhere between let's call it a few thousand, grams per mole to up to 1,000,000 grams per mole. So this range. And let's, for the sake of discussion, use something very simple for everybody to understand. What's the simplest molecular we want to chat about? Any pick? Just something really simple. Let's use our favorite. Polyolefin, polyethylene. CH2, CH2, and so on and so forth. Tons of CH2. Okay? So, we're going to do something really crazy here today. It won't exist in real life. We're going to come up with some idealized model to help us understand how to describe a chain. We're going to remove a lot of constraints, and we're going to set a lot of unrealistic assumptions. So unrealistic they don't exist, okay? So first, we want to study a single chain. So this guy, instead of a bunch of them tangled together. So imagine you have the ability to have a tweeter pick up one chain out of your water bottle, for example. Boom, we have it here, but you just can't see it, it's so tiny. So I zoomed in 1,000,000 times, that's what I'm holding it now. So we want to know how big that is. We need to describe a few terms. One of the terms is, we want to describe the length of molecular. Okay, that's the first technical term you will learn from this class is a fully extended chain. We need to describe it in terms of length. So in other words, so let's see. We can ask Zoe, help me. Zoe, can you pull one in? All right, so This is an example when we have a fully extended chain. And don't get me wrong, you can possibly make a polymer behave like this, but you need apply like what Zoe and I did. Pull it up, otherwise it won't behave like this. It will be coiled up. So the first easiest way to describe is how long a single chain if it's fully extended. So that's a term we're going to learn. It's called contour length. So this is usually written as LC. I will jump a little bit back and forth because I hate to stick to the note. So sometimes I'm not talking related to PowerPoint at all. But since now everybody requires to put up something, so I just put it there, okay? So how do we calculate the length of the chain? Like this. Let's say I have, use the same one as we talked about. What we said the other day. Did we talk about 1 million molecular weight of polyethylene? We ask, what's the coil size? So equally, I can ask you, if we fully stretch it, what's the length for it? So how do we get this length? Okay.
You'd have to know how many repeat units are in that
Yes.
molecular weight chain, and then calculate the distance in between each atom for.
Perfect, right? So we can do that just by understand the dimension of each segment of the chain. So, okay, my drawing is not going to be as pretty as this, but you get the idea. We have carbon-carbon, Amy?
In that image, is A the bond angle or the bond length?
Let me take a look. I think A is the length. I'm pretty sure. So we will go through that. So imagine if your bond is free rotating, so that's another unrealistic assumption, is bond is like free rotating, can be go any angle. It's like I had a bad fall, then my ankle breaks, so my hand can go 360 randomly. That's pretty miserable, but that's a good assumption for you to think about a polymer chain. So if it's really flexible, we can basically count how many carbon-carbon, if the carbon-carbon bond can be 180 degrees. Under assumption it can be freely rotates. So we can have some idea about what's the length, right? If we know how many carbons along the backbone, we can count how many C's along the backbone, and we just need to know what's the distance of these carbon-carbon. So let's define a few terms. If we define this L to be the length of the carbon-carbon bond, that's actually no. People can measure carbon distance or using the DFT calculations. So that's about 0.1535 nanometer. So I usually like to call it 0.154 or 1.54 angstrom. Angstrom is 0.1 nanometer, okay? So this is how long it is. To give you some idea, that's the distance between each carbon, and that's fixed unless you change the bond type, such as double-double bonds or triple bonds, or you install other functional group. But on average, if you have polyolefin, you think about this is about 0.15. All right, so come back to here. If we have 1 million molecular weight, how many carbons along this backbone? How do we know how many carbon-carbon bonds? If we know that, then we can solve the question is how long, if we fully stretch this polyethylene, how long that will be. So how many carbons? How do we know?
Take the molecular weight and divide it by the limit.
Okay, good answer. So let's see if that's right. So how do we count we know the molecular weight, we made it, but how about the molecular weight of repeating unit? So now we need to define a few extra terms. So if we look at the repeating, what we written in a polymer is CH2, a bracket, and so let me first tell you what this N is. You're probably going to learn very soon in polymer chemistry class. N is defined as degree of polymerization, or dP. That tells you how many repeating units are. So if N equals to 1, it's basically you're going to have a CH3, because it's chain N, okay? But if N equals to 10, you're going to have CH3, CH2, so on and so forth. This is going to repeat 9 times. Then there's CH3, okay? So all we need to do, count how many N is use total molecular weight, like how many total molecular weight is for a single chain. So how heavy you are divided by unit size of you will tell you how many you're repeating. Okay, so this we know, we said it's 1 million molecular weight of the polymer, right? So what about molecular weight of each repeating unit? So for each individual one. That's very easy. Someone help me, please.
28.
Oh, Zoe, where 28 came from?
The carbon and hydrogen atoms.
Okay. Yes. So we know the atomic number, molecular weight for carbon is 12. Mm-hmm. So we have 2 carbon in each repeating unit. 12 times 2 is 24. And we have 4 hydrogens. So where 12 came from, if you're looking at periodic table, this is very antique, but you know, I still use it. If you look at C, has a 12.011. We usually omit these 011. So molecular weight for a carbon element or an atom, one single atom is that. So you can use that to calculate what the repeating. So we have 2 times 2 carbon plus 4 times 1 hydrogen. Hydrogen is 1. So this is, Zoe is way ahead of game. She said this is 28, right? So we can now calculate what is repeating unit. N would be equals, for those who can see, N equals molecular weight divided by monomer molecular weight. Let's tell you how many repeating segments are. All right. Who can help me? I'm not very good at math using 1 million divided by 20. Anyone has a phone can help me? Please. Yeah. Should be, what's the number? Joseph? Huh? 1 million divided by 28.
35,714.
Okay. We just admit 14. Okay, that's good enough, close enough. It's less than 1% error. We're omitting. So 35,700 repeating of this N. So if I tell you each carbon, this bond is 1.54 angstrom. So how long my chain is now? Can I use 1.54? A carbon bond times I have 35,070. Remember, this is a unit of angstrom. Angstrom is just a unit. It's 10 to the minus 10 meters, okay? Is it right? Contour length, LC, would be equals number times, this is would be the bond, let me write the other way. The bond length L, which is no, it won't change, and times repeating units of N, we have calculated N to be 35,700. So we should be able to get the length. Is that correct?
If you ignore all of the bond angles along the chain.
That's it fully extended, right?
Huh?
That's the length when you are fully extended.
Yeah, any other opinion? It's a trap. Sometimes professor make mistake. And I made a mistake today, and you guys have to figure out why that's not right. Oh, Sarah?
Does it have anything to do with the in-groups?
Good guess. Yeah, N group would be one possibility. So Joseph raised the hand first. Let's
Don't
kill.
you have 2 bonds in there since you have...
Aha! Good try. Yes. So if you look at here, each repeating unit, so there's a carbon-carbon bond right in the center. Then I somehow have a carbon bond sticking out in the bracket, and there's another one. I can't count for 3 because I know this one is shared by next carbon. This one is also bonded shared by next carbon. So each one I can count as a half because it's shared with another guy. So in each repeating unit, we have 2 carbon-carbon bonds. So don't be as stupid as me, missing a 2. If you times the 2, that will tell you how long the total length of the polymer. Assuming it's a free joint chain. So Joseph, I'm going to ask you one more time to help me with the length. If you can help me calculate. You will know the total length of the polymer if it's fully extended. Okay? And
$109,956.
950, right? So 100.
No. 109
Oh, okay.
and then 956.
Okay. So this would be angstrom.
Right.
So we can convert to nanometer by moving digits. So I take away a 0. So this will be a nanometer because 10 angstrom is equals to 1 nanometer. And I can convert 1,000 nanometer to micrometer. So I can see this is roughly about 11 micrometer. 11 micrometer. Okay, that's when I stretch the chain fully. Okay, I want to use the rest of the class to show you if it's coiled up, how small that is. It actually differs a lot. To give you some perspective, if I blow this up to be blow it by a factor maybe 10,000, if this is 110 yards, like a football field, if I fully stretch the polymer, when it's coiled up, it's happened to be similar size of football. You can see how coiling up or extending changes dimension of the polymer so much. And we're going to do a quick calculation in a second, okay? So fully extended chain, everybody got it? How we need to understand that? We need to understand how long is the segmental of the chain, and then also understand how many repeating within the backbone. And how many repeating, we need to know the molecular weight of monomer and how many bonds in the repeating. Okay, but this is a very idealized. We didn't consider the bond angle. So what if in case the bond angle is fixed? So for all the carbon, so let's say for this polyethylene example, each carbon has 4 electrons. So it will form a hydrogen here, a carbon, and a carbon. To make this work, we actually call it sp3 hybridization, and you will for a tetragonal for these bond angle. So if I count this carbon bond to this is not 180. To be exact, this is a 109 degree. So if really some people want to more accurate, say we need to consider the angle, then the chain will shrink a little bit in the contour length because the angle is limited, it's a zigzag along the backbone. And how much difference is not a lot. You can calculate based on particularly the bond angle. So this you can multiply by a cosine, this half of this theta angle, you can get the contour length, okay? But in our class, we just simplify it to be bond angle is not fixed. It's going to be fully stretchable. Okay, so that's the easy part of the lecture. We understand 1 millimolecular weight when it's fully extended. What if it's now we start to let it form a coil? Like we showed it. Where does the cable go? Okay, here you are. What if it's coiled up like this? So how do we calculate the dimension? In order to capture it, let me get the eraser. We need to define a few terms again. So how do you count the size of a coil now? In terms of extended one, it's easy. We count where one end to the other. But if it's in a coil state, how do you count the size? I know Dashan going to tell me it's radius of gyration because he cheated. He already learned the second half. But if you are not Dashan, who never learned about it, how do you count the size of this? Can I measure the outmost to the bottommost? That's a possibility. But it's very hard to define where the end is. So actually we don't use that term. And the two of the terms we're going to learn in this course, one is end-to-end distance. So from one end of the polymer chain to the other is what we're going to use to describe in the first week, this week and next week, to describe how the size of the polymer. Yeah, Amy, please.
Is end-to-end distance like the full length of the polymer, or just like if one end is here and one end is here and the rest is coiled, like distance like that?
Yes, you are right, the second description. Okay. It's not fully extended. So now, if I'm the one wrote this up, the end-to-end distance will be roughly this long. If I toss it again, I'm going to roll it one more time. Oh, it's getting bigger. So how can we accurately describe the same molecular using end-to-end distance? So someone help me. If I want to use this term, we need to do something to it.
So you make an average? Or
sure, yes, we need to do some interesting things. If we need to count a representative of the polymer chain's conformation, we need to study its average behavior. Okay? So let me give you an example. A polymer is not frozen. It's particularly when it's dissolving in solution state, it moves around. And conformation changes. So it's like me extending the hand and all of a sudden my hand is tied together. So everything is living, it moves, changes. So the best way to describe a size of molecule is to count its average dimension over time. Okay? So we need to basically count average end-to-end distance. If I roll it 10 times, I need to count time 1, 2, 3, and I need the average. But physicists come up with a smarter way to describe it. So that's where we're going to discuss a few other terms. So the few other terms are related to the model. So first we need to simplify a model that is very easy for us to do our job. So what do I mean by model? So now let's pull our back to think about real chain. Use this one. In a real chain, your chain moves around, and it would never happen that your chain can overlap with itself. You know, what do I mean? If this coil is here, the next coil, when it's folded back, it can occupy the same space. Because physically, it's just impossible. You can't put two persons at the same space. So in order to do that, we need to describe a very simple model called idealized chain. So this chain is now idealized. It can do anything it wants, including folding back it to itself. And why we need this? Because we want to describe the first model of the chain we're going to talk about is called freely joined chain. Okay, freely joined chain. So this would be the model number 1. It's a polymer physics model, help you to understand how the chain behaves. So what is freely joined? Freely joined basically means we don't have any constraints. So let me come here. So imagine this would be the chain along the backbone. We omitted all the hydrogen, so this is just one carbon in polyethylene, next carbon, 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 so on and so forth. And we only draw 4 segments of it. So these carbons, we know the distance, so L is the distance. L will not change. But now the question is, this next carbon, realistically, we talked to you guys, this bond angle is fixed, right? It can't move. For a carbon-carbon angle, it's about 109. But we're going to break it. We don't care about that. It's idealized the chain. So your theta is a random number, can be 0 to 360. So it's behaved like 2 chains are a segment of carbon to next one, and then it's freely joined. It's like a rivet. You can swing it, and it can go any direction without any constraint. Okay, so free joint chain is really cool because although it's not ideal at all, but it is the simplest model, help you visualize how the polymer behave in a single chain conformation. So use the example that one. So then I can draw randomly on the board, as long as I can have segment has the same length, which I'm not trying not to mimic. Okay, so you can have things going around any direction because next bond carbon-carbon angle can be anything. It's not influenced by the previous one. So why? Because it helps us simplify a lot of mathematical model. So how do we describe the end-to-end distance? We talked about this in just a moment, end-to-end distance. So this is typically written as R, E, E. E is a subscription. So E stands for N, 2E means end-to-end distance. So this would be described, what is this distance between one of the polymer chain to the other. And next thing, I want to pull myself back and talk a little bit something different. We discussed about scalar and the vector. Amy, you have a question, please.
Is the end-to-end distance part of Model 1 or just like its own freestanding?
No, end-to-end distance is just a parameter we're going to count. It's not related to model. So if I have a chain, I'm doing randomly, okay? So this is star, the N. So this would be the distance RE. And one end of the chain to the other end, I count what's the value for that as end-to-end distance. That would be the size. We're going to calculate the size of molecule. So if you have high molecular weight, imagine the chain is very long. This value will go up. So it's a good way to describe how big your polymer chains are. So I asked a few questions on the first day of the class. Remember, I asked everybody about vector and scalar. So I'm going to reintroduce what the similar and differences, because those knowledge are important. I also uploaded a handout so that everybody can read it in the Canvas if you are not familiar with it. And if you still have questions about them, just reach out to me, okay? So let me describe you. What is scalar and vector? So for those who already know, so bear with me, because I know you guys are very smart. You already learned that. So let's do what? I need a volunteer. Who is good at drawing? Who? Oh, Amy, can you come to the board and help me? All right. So, can you draw a map, just the shape of state of Mississippi right here? Just the shape.
I'm really bad at geography. You've chosen my worst subject.
Oh, that's fine. All right. Good. I need the second one. Help me draw where Louisiana is. Come on, someone, please. Zoe, come on, help me. Then I'll teach you guys about vectors, etc. So just to draw roughly the shape of Louisiana. Next to it. Yeah.
Like right here?
Okay. All right, that's where the Louisiana is.
Like kind of goes like
Okay. I think we should be close. So, Hattiesburg is, I don't know where we are, probably here in the lower state of Mississippi. Then we have Hattiesburg, we call H. Then we have Jackson should be our left, so left or right? Jackson should be north.
Jackson.
It's not
East.
Yeah, okay, roughly. We're not a geology class, so we will be fine. But for those who haven't been to the Water Bowl meeting, you guys gonna go there next year? Water Bowl is in New Orleans, and I'm sure you're gonna go there quite a lot. It's a fun city. So where is N stand for New Orleans? Roughly here, right? Okay, last destination you guys should check out is Gulfport or Biloxi. It's on the coast, so right about, do I have a different color? Let's use green. Okay, so if I want to go to Gulfport to have some fun, hang out in beaches, I can drive there. Takes about 70 minutes. If you're not speeding, okay? 70 minutes? Roughly, that's about, what, 80 miles from H to G. We can write this. This means we start from Hattiesburg and in Gulfport. So H to G is a vector. Vector is some concept that has a distance and a direction. Okay? So it has two properties encoded in one. If I am just to tell you scalar, what is scalar is just a direction in, distance. It doesn't have the direction. So if I tell you drive 70 miles, don't tell you direction, you won't end up in Gulfport. You can end up in Jackson. So it's very important you guys understand where it starts, where it's end. And we typically draw arrow in where between these two numbers. So H. Arrow is usually on the top of your letter. So that describes where we start, where we end. And all right, so how long takes to drive to New Orleans for those who knows it?
2 hours.
Hour and a half.
Two. You're really fast, Amy. I drive there 1 hour 40 minutes. All right, roughly, okay. So that's basically the second vector we have. We can go H to N. This is vector tells you direction and where it is. Okay, so last thing, we can draw something G and N. So vector has some unique property because you can add the vector together and you can visualize it. So for example, if I use HG vector plus G and N, so you can see this would be arrow 1. Then the second arrow is starting where it ends, so it will point to New Orleans. So you can get H to G vector, okay? So this will give you two, when you add two vector, you can get a new vector.
H to N vector.
Oh, yeah, sorry. Yeah, my bad. Okay, so this tells you where you're going. So remember, it has directionality. If we just use a number to add, then it doesn't add up. Let's say this is a 70 mile, this is probably 120 mile, this is maybe another 70. Let's use that. If you use 7 plus 70, it's not equals to 120. Okay, so remember that. We can't just take the length of the vector and add them together. We need to consider direction. Did that clarify things? Okay. So there's also a few other parts unique about vector operation. They can be minors. So I can use this. I can use hn vector. So Hattiesburg to New Orleans, I can minus gn. So I can get h to g. In other words, I can point this arrow backwards and subtract it. Okay, one last thing, it's a little bit unintuitive, is you can use a dot product. Let's call it.
In this case, what does hn minus gn equal?
Oh, that will be hg. We'll start from h and then g. Because it's pretty much like a plus b equals to c vector. So you can, the operation is reversible. A would be equal to c minus b in that way. So you can move them to the other side of the equation and change the sign. So now the more important part is the dot product. So let me clear a little bit and show you what the dot product. And that's where could be confusing for a lot of people who haven't done any scalar and vector concept. So everybody, I'm sure you know what a multiply is, very easy to understand, and what a plus minus divides, etc. So dot product is interesting. So let's call it, this is vector A, this is vector B, and they have the angle because they have co-directionality. If B is not in the same direction, has a theta angle to it, when I use A vector plus B vector, that we have talked about, it will equal to C vector. And C will start from here and end where B ends. So this will be C vector. Okay? And you can use C minus A or B, etc. The other way you can do is A dot product B, and that's where a lot of confusion is. And for those who never studied it, I'm happy to slow down and explain. So this is a very special vector operation. It basically asks how much B has ability to follow A's direction. So it will be equal to A. The dot product no longer generate a vector. If you have plus plus, you always keep it. So it will equals to A. Then you have two lines around it. This operation means we're only going to take the length. We change the vector to scalar, okay? So this means we're going to take the length component times B times cosine theta. All right, yeah. Well, what this thing is, it's quite confusing, right? It doesn't mean anything. The dot product basically described, if you look at the second half, B times cosine theta. So cosine theta, if you draw a square, cosine theta is basically how much this length. The length of the green line is cosine theta. B times cosine. So basically it tells you how much B is following the direction of A. So this part of the B is in A's direction. Okay, so that's what dot product is. So we're going to use it in the later part of the course. So if you're not so sure, do a little bit Google, and I'm sure there's a lot of useful information out there, and happy to share with you more on that. But those are basic informations about vector. I want to take a pause. Any question regarding scalar vectors, etc.? Anyone? Anything? All right. Now we're going to come back to the polymer. We're going to come back to the polymer. And that's going to make it very easy to describe the polymer. Let's assume we have a polymer. Let's see. I probably have a slides on that. Okay. We can stay on this slide. Let's assume polymer has lots of carbons along and goes three-dimensionally. So that's why some of the bond may look longer. But imagine you have a carbon starts, the next carbon. We call it carbon 1, carbon 2, carbon, it should not be banded, carbon 3, and carbon 4. If we want to know the end-to-end distance, we can just simply get the end-to-end distance value. So how do we do it really quickly? We can do very complex operations. So let's do a simple way. We introduce a vector. So let's do some vector addition. Imagine you are the first carbon of this series. So you're carbon 1, and there's a carbon-carbon bond form. So look, you're going to look at carbon 2. You're going to form a vector. This vector defined as bond 1, L1, or R1. Let's unify and that's a vector. This vector has a length. Length we know. The length of this vector is bond-bond length. And it has direction where you come from first carbon to second carbon. All right, how about bond, second bond? How do we define the second bond? Same, right? So if we know where the second carbon and third carbon is located, we can map it a vector starting from C2 goes to C3. That will give you the vector of bond 2, R2. So on and so forth. If we have 100 bonds, we can have 100 vectors. So now how do we get, if we get 100 vectors, it sounds a lot, but not a lot. Remember, if we have repeating unit of 35,000, we need to draw 35,000 vectors. And end-to-end distance, if we introduce a vector, we just need to add all the vector together. We can get a vector start from first carbon to the last carbon. Does that make sense? So if we add bond 1 vector, remember not the length of the bond, but the bond vector. It has bond length and directionality in it. You can add bond 2 and add bond 3 vector, so on and so forth. If you have n, that means you have n of bonds along the backbone direction. That's going to be how many bonds there? So R1 to Rn. If you add together, this gives you end-to-end distance vector. Nothing fancy. This is exactly the same as I showed you. A vector 1, we go to Gulfport, then go to New Orleans. You get your direction from Gulfport to New Orleans. So this is the same here. If we add R1, R2, R, in this case R7, you get a vector of end-to-end distance. And I'm lazy. I don't want to write this long equation. So for the mathematicians, they use this particular symbol. So I'll explain what that is. So this is a sum symbol. That means we add all the elements together. Okay? This part, if I cover, I can't cover you. Imagine it's gone. Okay? So this is a sum symbol. This means I'm going to add a lot of things together. If I write And you can see there's something on the top and below that. Below that, I have I equals to 1 on the top of n. So these two symbols describe how many elements we're going to add up. Okay, so if you look at this writing, this basically is equivalent to I'm going to add all the r's together. This basically language for the mathematician says I'm going to add all the r's together. And I'm going to start with r equals to 1. So ri should have a vector sign. So this start with I equals to 1 means I'm going to start with 1. And I'm going to keep plussing r2, r3 until I end with number n. This is start and this is the end. So this defines how many bonds I need to add. And I need to change, keep increasing the number of I during the addition process. So let's do a simple one. If I want to add R1 to R9 vectors, I should add dot, dot, dot in between. Then this means I can write, because I start with 1, remember, so I can write I equals to 1, and I'll end I equals to 9. Or I can simply write 9 and Ri. So it will keep changing until you sum it up. Okay. All right, any questions so far? We got all the vectors, we ended, we have the end-to-end distance. End-to-end distance for the polymer of the bond length R will be equals to Ri, n equals to 1 to n, I equals to 1. It's a bit abstract, but you know what I mean. So add one bond, all the vectors, so this will be the final vector. So we talked about at the beginning, we can't take a snapshot of one single motion because this gives you the wrong end-to-end distance. Well, it may not be representative. Let me give you an example. So if I want to get a representation of this class on average height, weight, and you know everyone's then take average. I can't just pick one and show this is the average of the class, right? So we need to do average. So average has another mathematic signs. Average uses this double half arrow sign. So this means average. Okay. So if I have number 1, 3, 5, 7, if I take average of n, I can basically add average of n equals 4 divided by 1 plus 5, 7. That should be 4. Okay? So we can do the same thing. We just need to take average end-to-end distance. And when I first hear the answer, I was shocked. What is average end-to-end distance? I was shocked. If I tell you the number, you will be shocked too. What is the average end-to-end distance? Zero. What? 0? Why end-to-end distance is 0 for a free joint chain model? Daniel.
Just the law of large numbers and the lack of any bond angle constraint.
Lack of bond angle constraint. That's actually a very good answer. So imagine it's a free joint chain model. That means the bond can go any direction, right? It can go east, west, south, north. Free rotation. That means it can go anyway. So if I draw a long enough polymer coil, very long, if I found a bond is pointing north, I can always find another angle is pointing south. So the vector, it can cancel out each other. So average end-to-end distance, because we don't have no directionality of the bond angle, average angle, so let's write it, average angle of the bond should be 0. Right? Because it's a free joint chain. The first, let's use that model again. So where it starts, the next bond, this angle theta is random. It can point this way, but it can point this way or left. So you can always find some angle that can cancel out if it's free joint chain. So average end-to-end distance is 0. That might be confusing. Then we screw. We totally screw. I told you that we can use end-to-end distance to count the size of molecular, but now you tell me again and no. Are you teasing me? Where did my tuition go? Bear with me. It's just half of the story. So we can do some tricks to that. So some of the tricks we do in the polymer physics is we can count average vector. We need to count average scalar because scalar is the distance. So as long as we can convert this vector to scalar, we should be able to get the distance, not distance plus directionality. I emphasize it one more time. The average distance plus direction for a random free joint chain is averaged out. It's always, because the lens can point in a different direction, they can cancel each other. But if it is just a scalar, we can get a distance, and that's what we are going after. The simplest way to convert it to a scale from a vector to scalar is called self-dot product. Okay. So from vector to scalar, self-dot product. So if I have vector A, I want to convert it, I can use this conversion sign to get a scalar A, or I can use self-dot product and take a root square. All right, so for the bottom part, I'll show you why. You can use a self-dot product to convert into a scalar. So dot product equals to scalar of vector A times scalar of vector A and times cosine theta. Right? That's what we talked about just a moment ago. All right, now I have a quiz for everybody. So what is theta in this case for self-dot product? What the theta angle is? 0. Good job. Yes, because we are talking about two vectors pointing in the same direction, so this theta should be a 0, right? It's two of the same, vector A times A. So cosine 0, for those who know, is equals to 1, so we basically can take out this part. And if we now get a scalar, the number of the vector part square, because it times itself. So in other words, we can get the end-to-end distance using a very simple relationship is we use a self-dot product to solve this challenge. All right, so don't be scared with all those maths. I know it's for chemists it can be daunting because when I first started, I don't understand a damn thing of these. But we slowly explain to everybody what each part means, right? We explain what this sign is, these two things. average, right? We explain this is a sum. Oh, but why there's 2? Okay, it turns out that you can have as many as you want. So let's explain that one more time. So what we explain, if we want to have A1 plus A2 plus A3, so on, AN, you can have sum of I equals to 1 to N and AI. But if there's more than 1 adding together, you need a different term because you can't have it. What if it's A1 and B1 plus A2 B1 plus A2 A3 B1? So you now have 2 variables. Then you have A2 B1 blah blah blah. If you want to add all these large numbers together, we can use this term. I equals double sum function. So this is I and this is J, N, and we can just say, let's see, R, Ri, Rj. If we have 2 functions under the same sum function, we can have double sum. So in other words, this basically sums up to be a matrix. So you have A1, B1, A2, B2. So A2, B1, so on and so forth. Then have A2, A1, B2. Okay? All right, I'm going to use the next 10 minutes to wrap up and give you some conclusions for today's class about end-to-end distance. We walked quite a long way, right? We talked about average of vector, we talked about average of scalar. So we finally find a way to describe end-to-end distance, square. This is what we are going after. I want everybody to think a little bit how to solve this problem. Let's pause a little bit. End-to-end distance square. As long as we can get end-to-end distance square, we can count the end-to-end distance. Like the core I showed you guys, we can get that value. So how do we do end-to-end distance square? Well, that's pretty straightforward. Everybody has done it. Square just means it times itself. So all we need to do is use REE, a vector, times end-to-end distance vector. We can get the result. Right? That's all we need. And
is that a dot product
yes,
between the two?
yes, it is a dot product.
Is it still the average?
Yes, we need an average. So if you look at here, that's the same writing. So end-to-end distance square equals to Rn, because RE basically equals to Rn add together. Each Rn end-to-end distance is equal to, remember this R is a bond, so Ra is a bond, so each bond add together. So we just need to solve these complex equations. And as I said, I know that everybody comes with different background. I don't expect everybody to be like math savvy. When you graduate, you can solve these complex equations. You don't need to. I'll explain how this works. So you just need to understand the conclusion and understand the physical meaning. So we can, Rn is equal to bond vector, end-to-end vector equals to bond 1 plus bond 2 plus bond 3, etc. So this Rn is equivalent to the sum of each individual bond. Okay, so each individual bond add together times each individual bond. So how do we jump from this part to this part? Not hard at all. So everybody has any idea what a matrix is? Have you guys studied any of the, heard about the term? If not, that's not a problem at all.
Sorry, I have a question.
Yes, please, Jay.
I mean, the average of RE times RE is equal to the average of IE times the average of RE. It's the same thing? I mean,
Oh, that you don't need to. The bracket should be here.
yeah.
Yeah. But let's talk about vectors. So if we have vector A times, so I'm going to introduce a little bit different terms. So let's use 4. Just take the first of 4 because that's easy for everybody. So if we have 4 vector times 4 vector, how many components it will be? Oh, this could be as simple as A plus B times C plus D. Let's use this one to start off. Then you guys can understand better. So this equals to, I'm sure everybody learned it in your class, A times C plus D plus B times C plus D. So you would end up AC plus AD plus BC plus BD. So there's 2 here, there's 2, so you should have 4 different terms. And now going back, here is a full, here is full component. So when you add them, when you time them together, you should have 6 components. And it's easier to write it in a square matrix because it's 4 by 4. So we can write a 4 times 4 matrix. Matrix is basically means you have a box, has 4 vertical slot, 4 horizontal slot. Okay? So for the first one, we would end up A times A, you can put it here. Then we should have A times B vector, A times C. So it's kind of pretty because it's symmetric. This would be the first component, use A times to each individual of it. Then second row of the matrix would be vector times A vector. So B times B, and B times C vector, and B times D vector. And I'll write everything out. So the third row starts with C times A vector, C times B vector, C times C vector, and C times D vector. And last row start with D vector times A, D, B, D, C, and D, D vector. Okay, so you generate a box of, a row of 1, 2, 3, 4, a column of 4, and you have 1, 2, 3, 4 rows. 4 column, 4 row. Okay? So if you're really bored about writing a matrix 100 times 100, the easiest way, I'm not gonna do that because my arm probably broke. I barely survived writing 16.
The first example you gave, the A plus B plus, or times C plus D, are those all vectors?
Yeah, it doesn't matter if it's vector or scalar, they will be the same. It's just simple math.
Yeah.
You should, some of you should know. So if we have 4 by 4 vector, we have 16 number. And it's hard sometimes to write so many, so we just use this to describe it. This is what I equals to A to D, and J equals A to D. And we can write I, J vector. So this double sum is basically tell you we have ABCD and ABCD matrix and has I and J in there. It's the same as here. So if we use the same as different I, Rj, we will end it up exactly the same as a matrix. I will not write the whole matrix, but imagine if you have vector A1, imagine now RE vector times RE equals to be R1 plus R2 plus Rn times another R1 times R2 all the way to Rn. Okay. So this would generate a matrix look like this. You have 1, 1 here, 1, 2, and R1, R3, so on and so forth. So we basically write as this particular symbol. And we can actually group this particular matrix into an interesting way. If you look at this pattern, if we draw a diagonal line along the pattern, we will find some interesting phenomena. So this would be A times A, B times C, B times B, C times C, D times D. Or in the vector parts, we will have R1 times R1, R2 vector times R2 vector, R3 times R3, so on and so forth. You would have a diagonal that made up of the vector times itself. And there's a total number of n of them. We can call them the self-term or step dot product into itself. And there's another, for those who are not belong to the here, so this R12, R13, etc., or R1, let's write a random one, 3, 5. These are not the same number, right? So all the data off diagonal, we can call them generally, it's a cross term, and can be described by I equals to 1. And as long as J is not equal to I, they all belong to here. For J equals to I, they belong to the first part, self-term. Okay, so it turns out this is self-product. We know the value. Self-product Rj, a vector, times itself, equal to its vector scalar. Yeah. So the length of this is basically bond length. And you have n of them. So this term should be equal to n times L times L, so NL squared. And for anything that average of Ra times Rj, where they are not the same, their directionality is lost. So you don't have anything. The average of this will be equal to 0. Okay? So for all these non-self term, because there's no bond directionality, the average of cosine, the last bond to the next bond, they don't have anything related. So average of bond angle will be 0. You ended up, for the self term, because theta is 0, you end up, this will be n. And we have bond length L times L. This gives you the conclusion of the first part of the lecture. The end-to-end distance of the polymer comes down to NL squared. Okay? Remember their end-to-end distance square average, okay? If you want just get REE, you need to take a root square here. So I'll give you guys a minute or two to digest, and I'll explain the physics of it. And then I'll recapture today's lecture, give a summary. Okay. So the end-to-end distance, Amy, yeah?
The thing says uncorrelated, the average of theta equals 90. How do you get that?
Oh, so if I have a bond like this is a bond, let's call it R1, this is R2 vector. So if it's free joint chain, that means the next theta versus original direction can be random, right? Is it random? So it can be any possible directions where the next bond is pointing to. Correct?
Yeah.
If it's pointing in the original direction, this is 0, theta equals to 0. If somehow is opposite, this theta means 180. If somehow is stuck in between, it's 90. So how do we get 90? Because we take average of this direction of the bond. It can be this direction. So it ended up, all the bond will average out to perpendicular direction. That means they don't have directionality.
Now this only works where it reduces to NL squared when it's freely rotating,
Yes.
and when you don't have freely rotating, then you're going to have an angle.
Yes, then average of bond angle not going to be 90. So this assumption don't hold. So in other words, the end-to-end distance square, I want to emphasize a few times, there is a square here, equals to NL squared. N is number of bonds. How many bonds along the backbone? L is the bond length. Number of bonds. So this is just tell you, like we did in the other one, Joseph helped at the beginning, count how many carbon on it. L is just the bond length. Okay, let's take a look at the other value. We talked about contour length, LC, at the very beginning of class. This would be equals to number of bonds and times the bond length. Very simple. So N times L. You might say this is bigger because we didn't take a root square. So this is a not fair comparison. If we take a root square of REE square, so this will be equals to REE average. Okay, this will be N power of 0.5 times L. That's your end-to-end distance, how it depends on the bond, number of bond and bond length. That gives you the dimension, okay? So actually how big that is, let's do a math. We already erased it. Joseph, do you remember what is the number of bonds we have?
35,700 times 2.
35,500, right?
700.
Okay. So this is the number of bonds. So RE will be equals to N of half times L. So N is going to be equal to root square of about 71400 bonds times L. So can you help me take a root square of 7014? Then we will tell you what's the end-to-end distance for a coiled 71400. It should be
71400
yeah.
times what?
It's a root square.
Yeah, 267.
267 times 1.54 angstrom.
Is 411.
411? Okay. So that's what the end-to-end distance of the polymer. 400 or 41 nanometer for the polyethylene. 41 nanometer versus the other number we talked about, microns. It differs by almost a factor of 300. When it's coiled up, the dimensions shrink by a factor of 300. If you take a football field, you shrink it by 300, that should be closer to the football size. So the polymer actually shows so much difference in dimensionality. The end-to-end distance is a good way to give you some idea what the size. And when it's fully stretched versus coil, you can see it varies quite a lot. Okay, so for this, I'm now gonna wrap up for today's lecture. We talked about the beginning of the polymer physics. We use the polyethylene as an example to show you guys how to get the dimension of the polymer coil when it's stretched and when it's coiled. And in order to make it work, we made a lot of assumptions, and we start with one first model of the semester is a free jointed chain. So in this case, your chain has defined length, but the angle is random, so it can go any direction. So we use that model to give you some idea if it's a million molecular weight polyethylene. If it's fully stretched, I forget the number, it's maybe 10 microns-ish, right?
11.
11 micron, right?
Yeah.
Okay. When it's shrink, it's go down to 41 nanometer. So it's quite a big change. And we introduced the concept of vectors to help you to understand how to get the end-to-end distance because it's much easier. So we showed you guys how to add the vectors together. So for those who want a little bit extra work, take a look at the handout and understand a bit what the vectors stuff. And with that, I think I can also announce the winner for the first classes guess. So it should be 30 nanometer is closest, whoever voted for that. Everybody still remember your vote? No? All right, so congrats to those who guessed it right. Now you know why. Okay,